All right, hello you guys, Britt here. Hey, I'm going to do something ambitious today, as you can see from this monstrous craziness here. But I think it might be helpful to you. I may go for a little longer than normal, maybe 30 minutes or so, but you know what the deal is, so if you like that, you can stick with it. Okay, so first thing today, this kind of reminds me of The Beautiful Mind, where they had all those strings, and then when they came and saw it, they thought, oh man, that person's crazy. So when you see all this stuff, you know someone in here is crazy. Anyway, what I'll first show you is some books that we're going to probably want to use in the future on some stuff we're doing. This is called Ceramic Glazes by Parmalee and Harmon, 3rd edition. This is a super good book, which we'll talk about. It's Ian Curry's Stoneware Glazes. Here's another super good book. There's a lot of super good books. The Practice of Stoneware Glazes by Daniel Montmolian. I don't know if that's how you say it, but that's how I said it. Anyway, Revealing Glazes is also good. Cone 6 Glazes by Michael Bailey. All these things, these books are a little more on the technical side and are going to help you to manipulate your glazes, understand them a little better. Even if you use the same glazes, it'll help you to know what's going on. So that's the goal of this. And today we're going to talk about glaze software. So we'll start, we're going to try to do this systematically. We're going to start where we were yesterday with the structure of the Unity Molecular. Then we'll look at some glaze software things, the Silica and alumina grid, some limits, more limits up here, positive and negatives, the Stull chart, etc. So we'll get going on this. The one thing I do want to say is these glaze software, just because I'm talking about them or being somewhat critical of some things, doesn't mean they're not fantastic. So I use them all the time. I've been using them for 20-something years. In the old days, we got Hyperglaze with Richard Burkett. I use Matrix a lot. Lawrence Ewing's, that's from New Zealand. Tony Hansen is outstanding. He has the Digital Fire database is just outrageously fantastic. And then he has now Insight and Insight Live, and he's redoing these now. I'm not sure when they're coming out, but he's redoing them to be better on the phone and stuff like that. I'm trying to think of other ones that I've used in the past. There's so many of them, but so they're good. So if I'm saying things, that doesn't mean I'm critical of these people or of the software in general. All of these things facilitate your looking at glazes. So if you are an artist and do not like this stuff, you want to just get a recipe, mix it up, that's fine. But some people are scientific-minded, engineer types, and they like to know what's going on. So we want to have a way to look at glazes that way. Okay, for me it's like playing music. Some people play with sheets of music. They can read music. Other people are like where we live, there's a lot of people who do the oral tradition. So they just memorize music. People who do shape notes. So all these ways are ways of doing music, and you don't have to do any of them, or you can do many of them. So that's up to you. I found out Paul McCartney doesn't know how to read music or write stuff down. It's like, wow. When you find that out, you then understand more about how people can do glazes in the most magnificent way, but don't know all of this. And yet, if we can blend those two together, it may be good or not. All right. So you got those books. Another thing that is good is this one here called Glaze Stability by John Hesselbreath. You can Google it online and print it out. It's a great analysis of limits and how they took limits. They started working on those because they were trying to get lead out of glazes. So it's an excellent overview. And this is the Stull paper showing how Stull came up with his diagram. And the reason I talk about that is because Glazy uses Stull as their main diagram. All right, I think I did that. Now let me bring this camera up here And maybe we can just go linearly like this. All right, so what we've got here is this is where we started yesterday. So we've got the R2O, that's the alkaline fluxes, sodium, potassium, lithium. We got the alkaline earth, calcium, barium, strontium, magnesium, zinc, RO. And then we'll have our refractory, which is alumina, our glass former silica, and boron. And by the way, last time I forgot to talk about phosphorus, but that's okay. We got a lot done. All right, so here's the first one. I want to show you the printout that Matrix does. It's very nice. Each of these software does different things. Like, for instance, he has a lot of fields. This one is the silicon alumina ratio. He does the coefficient of expansion. He also does surface tension. And then he does percent analysis, Seeger. And I like this one. This is the limits, and he'll put a little bar graph if you've exceeded. So this one is exceeding the limit in calcium. This one's on the low end of alumina, in the middle of silica, etc. And then he's got this nice grid here for the glazes plotted on the silica alumina grid. Okay, that's super nice. Then we've got the next, so that was the leach clear recipe that we talked about yesterday. I wanted to just show you that. Now what I did was I programmed in the Hansen 5x20 with the same ingredients, G200, etc. Then I did it in Insight and I did it in Glazy. And all these numbers are slightly different. And that is because it depends on what their analysis is that they've loaded into their machine to print these numbers out. So they can all be slightly off, but they're probably pretty close. For instance, this one says silica 0.33, this one says 0.35. This one says, oh, I'm sorry, I said that wrong. 0.33 silica, 0.28 silica, 0.38 alumina, 0.35, etc. Okay, so now let's look at what Tony does in Insight Live. This is Insight Live printout. He's giving you the silicon alumina ratio. He also gives you a silicon and boron ratio, because that is a boron is a glass former. So that can inform the way you are looking at how glossy a glaze is. Okay? Then this is the R2O breakdown. So usually they just go like that. It's a 0.2 to 0.8. And then he has an expansion number, loss on ignition, of course the percent, and UMF. And Glazy now has a silicon alumina ratio. They have this R2RO, and then this analysis. They also have an extended analysis, which they're just starting to use, but could be good in the future. We'll see. Okay. All right. So we did that pretty good, I think. So now what I'm going to show you, this is what we used to do in the old days. We had a silica alumina graph. We would draw these lines. This is a 1 to 5 alumina to silica, and it could show there's matte glazes here, or satiny mattes, and here might be mattes. So somewhere in there is going to be satins and mattes. Then there's also other lines you could draw, 1 to 10, 1 to 8. Over here's 1 to 12. I didn't draw that in, but that is a way to show like silica mattes. So this was a way that we used to look at glazes, and we used this limit. This is Ron Roy and John Hesselberth's limit for cone 6 glazes. And if our glaze fit in here, we would think that it would be a pretty good functional glaze, or we would predict that it would be. Okay? So let's see. So now what I will talk about is, this is cones. I don't know if you know how cones were developed, but they had an alumina silica ratio of 1 to 10. So 0.5 alumina, 5 silica was cone 5. This was cone 6. So you can see a pattern there. So that went up the 1 to 10 line. And alumina controls the heat. Okay? So I just thought I'd throw that in there because we don't have enough to do. All right, now what I want to do, in the olden days, we used to use limits. And I plotted these for you so you could see, like, this was insight limits. So this is low fire, mid-range, high fire. And this was Green and Cooper. Same deal. Matrix, same deal. You can see how so a cone 10 glaze can have so much alumina and silica, and as you go to 6, you need less, and as you go to 05, you need less because it's hard to melt alumina and silica. Okay, and then these were Val Cushings for a clear and glossy. Look how large they are. And these were valves for satin, and these were valves for mattes. Okay, now you can see that Val Cushing, so here was the problem in the olden days, is we couldn't pick which limits do we want to use. It's so confusing, but it's really not. Like Val was an artist, you know, he worked with artists, and so they had a wide range of limits because they were all over the place. If I was doing just functional work, I may be tighter. Like this one is much tighter. If I did like Ron Roy's was super tight because that's all they were doing was cone 6. Okay, now let me come back to these charts. So now Glazy is using, this is the Stull chart. So that's an alumina silica grid, and what happened was in 1912, this guy Stull was doing some tests of tiles, fired to cone 11 with a 0.3 alkaline flux, that's R2O, and then RO was 0.7. He went up about 50 degrees C per hour. And the thing about that is they've used this chart now, they've adapted it, and they use it exclusively on Glazy. Okay, they also, like the Matt Katz, he did a article or a paper on how much boron, and they like that to be at 0.15. Okay, so that is here. I drew it on here. So what the problem with this is they're trying now to use it for all cones, not just cone 11 and not just 0.3, 0.7. They're using it for everything, and that becomes a problem because it's listing things here like crazed, matte, and semi-matte, and all this is so crazing is clay body dependent. So you can get crazing. You know, you can imagine if you had 100 clay bodies or 1,000 all over the world, you cannot guarantee that they're not going to craze because you also don't know what temperature they're fired to and how long they're soaked. Because in when you're firing a kiln, there's silica in the crystal form in a clay body, and that has a high expansion contraction. And then when you heat that up and melt it to a glass, it has a low expansion. So the hotter you heat it, it changes the expansion contraction and therefore changes the crazing. So to me, the problem with this chart is not that it's not very nice, and it looks super good when you see your thing plotted on there, but it's over-promises. So even these semi-matte and matte are not always correct because that depends on cooling. So if you have a real long cooling cycle, you may have it may be way over here the line. So if when you're doing this, you are flexible in your thinking, erase that word crazed, or if you know that maybe this crazed line is going to move up here and be just here, or the matte line may move here. So that's something we're going to talk about when we get into stuff with Ian Curry here's the silica alumina grid he does, and he'll do testing in all these squares going up, different ratios of silica to alumina. And then he'll show here where he shows how the chart is different at different cones. Here's 10, 12, and 14, and the matte section is here, and then by the time it gets so hot, it just moves down. Okay, we'll talk a little bit more about that later. So let me think where we're at now. So in terms of the problem with the limit idea is that it's confusing which ones to choose. And then when these here are just the silica and alumina grids. So over here now is the materials like sodium, lithium, calcium, etc. It'll tell you how much you want before you start having problems. So they're giving you a target to shoot at, but not necessarily it's not written in stone. The problem here is like they don't have anything for lithium, they don't have anything for strontium, they don't include bismuth or phosphorus. So it's kind of limited in that way, but still good. What was I going to say? I was going to say something else. Okay, so those are then what I did was I took, this is the Ron-Roy limit for cone 6. And so if you have Glazy and you're looking on there, you're saying, where is a functional cone 6 glaze? It's not all of this. It can't possibly go out into infinity. So there needs to be a top end here. And there is, but they don't really talk about that. But what happens is if you plug in the Ron-Roy limit into Glazing, I'm sorry my chart got a little wet, but you can see how it sits right there. So what would be nice on Glazy if they had that on there, that way beginners could have an idea of where to operate. But just so you know, you can do that yourself. And what I've done over here, I did it myself. Here's the Green and Cooper limits. I put them on the Glazy chart. You can see they fit right in this axis of good melting. And then I put just the cone 6 in here so you could see that isolated. It perfectly fits in there. So that's that deal. I did the same thing here with different ones. This was matrix. And anyway, that's it. All right. So now let me say this. Well, here's the good things about software. It's great for record keeping. It's great for sharing recipes. It's cheap. Even Tony Hansen's is super cheap. I don't know if it's like $20 a year or something. You can establish a community in Glazy. Glazy is an awesome site. It's constantly changing. They have a group called Glazy Support where these people are just working on problems, changing things. It's probably going to be the case that as soon as I get this video out, it'll be a completely different product because they're continually getting better, adding things, changing things. So that's super good. And you can put pictures up there and you can learn things on the site. They have a help section. Another great one, like I said before, was Digital Fire. Super good for education. All right, the things I don't like about UMF is there's no consideration of material. They like to say things, people who like Unity Molecular like to say things like, it's all chemistry. It's not all chemistry. Some of it's physics, the physical nature of the material we use. So if you use wollastonite at a certain mesh size, which they don't talk about in these, it's going to melt different than whiting, which is a very fine particle and goes into a glaze melt real easy. So everything is, to me, dependent on firing. So they don't talk about that at all either. Another thing about materials is there's variations in materials and input. So if you put material in Glazy like dolomite or Custer feldspar, somebody else may have a different version. They try to do that in Glazy, let you choose, But sometimes, you know, potters, they don't know where their materials came from. Someone quit pottery and gave them all the materials, so they're uncertain. So oftentimes we have an illusion of accuracy with the software because we think it's molecules and atoms counted down, etc. But if we don't have the correct material, we don't have the correct analysis. All right? Now, these are not monumental things I don't like. They're just things to think about. Another thing they don't talk about is glaze thickness. So if you put a glaze on real thin, it may not craze. If you put it on thick, it may craze. So all that matters in pottery. Okay, so I talked about, there was a whole bunch of stuff about Custer in about, I don't know, 5 years ago, where the analysis on the website was not what was in the actual material, and that's why a bunch of pottery was cracking, because all the clay manufacturers use Custer to make their clay bodies, and it lost 10% of the potassium. Unbeknownst to anyone. So just in case you don't know, anybody who did glaze analysis in the past 20 years and used Custer, and those numbers was way off on their analysis because it was incorrect from the factory. Okay, so another thing is cones and firing. If you fire to a different cone, what if you fire to cone 5? These only list 6. What if you fire to cone 3? What if you soak it? What if you do a long, low soak? So these are not included in Unity Molecular. All right? So the problems I had with Glazy was that it just overpromises in terms of this crazing line and exactly where all these things are. It doesn't explain it to people, and there's also no top end. They need to have a end there. But you can do that on your own now that you know this, and then adapt your thinking when you're looking at your... Okay, also they like to treat all the RO and R2O as the same. Like RO is calcium, magnesium, barium, strontium, zinc, and those definitely are not the same melting. So zinc is a much different melter than magnesium. Okay, and I already said it's all cones. Okay, here's a few things I wanted to say about this was in terms of the material you get. So what Derek did on Glazy was to get different potassium feldspars with EPK and put them in here and then plot them. So you can see the variation just within using potassium feldspar. It's a very large area. But they're acting like just going a little bit over this line, it's going to make all the difference. And it might, but it also might be your materials off. Okay? And then they like to talk about 0.5 boron. Well, this is from a paper Matt Katz did at Silica, and so he's saying that 0.28 degradation in a dishwasher at 60 cycles is acceptable at cone 10. So he then put his cone 6 glaze, which had a 0.3, 0.7 ratio, and then he kept adding boron, and sure enough, 0.15 is the best, in quotes, but in fact, if you went up to 2.8, almost all the way up to from 0.1 to 2.8 is acceptable, and as is this one at 0.5. So to me, this is not definitively saying that 0.5 is the best. What it says to me is boron makes stronger glazes than cone 10. And here's another one that's kind of inherent in the Glazy ethos, because Matt's involved with them, is that he has this O4 test and then claiming that 0.5 boron is the best. But if I look at this, I have problems with this, because this is saying that 0.3 to 0.7 RO is this yellow line, and it started here, and when he did the dishwashers, it went to here, and then here. This means it got shinier because the dotted line is where it is, 0. Well, it cannot get shinier. So to me, this whole test has to be redone because that is not correct. This one is way below the line and then jumps up. So something is wrong here with this test. Also, there's no 0.2 RO, 0.8. That presumably would be right in here. And now that's telling me that 0.3, 0.7 isn't the best. Maybe between 0.1 and 0.3, including 0.2, is good, acceptable. Okay, and also the problem here is it doesn't go out far enough. This could probably go out further if you didn't stop here at 0.55. So to me, that is not, I need to see more research before I can follow those rules of 0.5, because I've done many tests with cone 6 glazes, and say, for instance, if I was using this chart and I was trying to keep it at 0.3 to 0.7 for cone 6, I would get crazing, because 0.3 means I have a lot of sodium in there. And so I may have to reduce, that's the highest expanding oxide. I may have to reduce that to 0.2 and increase this to 0.8 to stop the crazing, in spite of this line telling me. Okay? And this is also, and Derek has done in Glazy, he did some tests of cone 6 clears and found that the best ones here were 0.8 boron, 0.36, and I have some glazes here that are super good. They're 0.36 boron. So what I liked was maybe going back to the limits. I still trust these limits more that people developed over many years, that maybe boron up to 0.45 is not bad at cone 6. Okay, I'm looking over this and I think I may have done it. There's some cone pack for you. All right, kids, you enjoy yourself today and take a rest, and we'll do it again.